good afternoon. I will take you from now to 2050 in another scenario study and project. And I'm talking in this session on hurdles, but I'm hoping that I can already show you that there are also quite some opportunities, which is in fact the next session after the break. So let's get started. Working at VITO Energyville indeed. Energyville is a collaboration of the institutes that you see on the bottom of my slide here. KU Leuven, two universities, KU Leuven and University of Hasselt, but also VITO and IMEC. So let's get started. First of all, I have also a QR code. So if you want to scan this, it brings you to the website of our Paths 2050 project. Project that we end beginning of this year with a lot of sensitivities and scenarios, but also methodology reports, so you can have a more detailed look into all results of the presentation that I will give you today. I think I don't have to tell you, when you want to make scenarios looking at 2030, 2050, you need to make a lot of assumptions to do this. And in this slide, I want to guide you through the list or the key assumptions that we have taken for this study. The model we are using is a cost optimization tool, so it searches for the least cost to bring you from today to a 2050 situation in a net zero context, so without emissions in Belgium. So first of the first assumption we took is that the industrial output levels in Belgium stay as we see them today. So we still produce steel, we still produce chemicals in Belgium. That's a bold assumption. Why did we took this one? Because we turned the question around. What is needed in our energy system to make sure that we can still produce these industrial products in Belgium? For the refinery sector, this is a different assumption. That's the sector where we aligned with European scenarios as well. So we assumed a decrease in the fossil output, refinery production with 43% in 2050 compared to 2014. There's also a shift towards more feedstock, of course, but fossil fuels will be less needed. We did a detailed study on the renewable potential in Belgium, and looking at today's PV, we are at 6 gigawatt, a bit higher. We can go up to 100 gigawatt in Belgium, only using the rooftops in Belgium. So that's a very sharp, very high potential we still have available. Looking at onshore wind, we can go up to 20 gigawatts. And today we have almost 3 gigawatts implemented in Belgium. Offshore wind will be one of the key technologies. Unfortunately, we only have a little piece of North Sea to our potential, and that gives us an 8 gigawatt of offshore potential. Also a sector where we saw in latest reports, latest press, that there's quite some issues in scaling it up at the pace with the high interest rates we see today. Going a bit further in the offshore wind in the North Sea, we see a total potential of even up to 300 gigawatt according to the latest report. And in one of our scenarios, we also assumed that Belgium will have access to this offshore wind outside of the Belgian North Sea, with a direct connection to, for instance, Doggerbank, the large offshore area up Denmark and the Netherlands. Electricity import is a fixed assumption, so the grid infrastructure is increasing from 6.5 up to 13 gigawatt in all scenarios, and that's aligned with the European and SOE scenarios. Carbon capture, utilization and storage is one of the other key technologies that will be needed to decarbonize. As Belgium, we don't have access to the storage potential, so we need to work together with neighboring countries, Netherlands, Norway, for instance, to store the CO2. But there is a lot of interest captured from the industrial sites, like in the port of Antwerp, North Sea Port, and Ghent. Import of green molecules, one of the other assumptions you need to think about. Within Belgium, we are working towards being or becoming an importer of clean molecules that can be hydrogen, but also derivatives like e-methane, e-methanol, but also ammonia. And we made assumptions on different costs for the import, looking at what is the role of hydrogen, of these molecules, in an energy system at different cost assumptions. And last but not least, new nuclear was also one of the technologies we included. We looked at small nuclear reactors, or small modular reactors, as they are called. We know that today there is a lot of research going on. The Generation 3 nuclear is proposed to be operational by 2035. We only looked in our scenarios at a technology that is generation 4 nuclear, so only allowed it by 2050. So let's have a look together at the 3 main scenarios that we distilled from all of these assumptions. So in the central scenario, we made a good mix of the technologies and assumptions that I just showed you. On the left-hand side, you can see the electrification scenario. So in this scenario, we started from the central scenario, but on top of it, we allow more offshore wind, directly imported in Belgium, and we also allowed this nuclear technology by 2050. On the right-hand side, the central scenario, the clean molecule scenario, again starting from the central scenario, but on top of it, we import hydrogen at a lower cost of 1.7 euros per kilogram, which is quite aggressive, as you've seen also in the previous presentation. And we also limit the access to CCS, to carbon storage, to 5 million tons per year. So now let's dive deep into the results, and I'll start with the final energy demand from Belgium. So you'll always see the same type of graphs, 3 bars on it, central scenario to the left, electrification scenario in the middle, and clean molecules to the right. Results for 2020, 30 and 2050. So total final energy demand in Belgium today is about 350 terawatt hours. That's excluding maritime and international aviation. When you look at the main results from the 3 scenarios, you see that for all 3, the final energy demand decreases by 1/3 due to efficiency. I'll go a bit deeper into it in the next sector slides. But also that the electricity demand in the 3 scenarios more than doubles. So electricity will be the main driver to decarbonize in Belgium. Not only in Belgium, I can already tell. It's the same story, of course, when you do these scenarios in a European context. Let's now have a look at the different sectors. First of all, the building sector. Keywords here are renovation and electrification. You immediately see that the 3 scenarios, although they have very different assumptions, show that the final energy demand follows a very similar path in the 3 different scenarios. So, first of all, 2030, we see a complete fossil fuel phase out and a shift towards 1.5 million heat pumps. Knowing that we have today about 600,000 heat pumps installed in Belgium, this is quite an achievement needed to go on track or to be on track towards 2050. By 2050, we do see that apart from electrification, so there's also natural gas phase out, we also see that more than 800,000 homes can be connected to district heating fed by geothermal energy or by waste heat. The heat pumps on its side also provide a lot of flexibility. So flexibility that is needed linked to the renewable electricity system or the uptake of renewables for the electricity production. You can also see that hydrogen plays no role for the heating of buildings, of houses. Looking at the cost-effective results of our scenarios, the model shows that there is no need for hydrogen for heating of houses. Transport sector. Keyword here as well, electrification. I think that was already clear in the previous presentations as well. By 2030, we see that more than 2 million electric person vehicles are invested in the Belgian context. When we go to 2050, a very sharp decrease in final energy demand can be seen. Electric vehicles are up to 3 times more efficient than fossil fuel cars, so more than 75% of final energy demand that is decreased. Complete phase out of fossil, but of course large uptake of electricity in this sector. We also see that freight transport is electrified. It takes longer, the model waits until 2040, even 45 for a full electrification of freight transport. But also here, the role of hydrogen is very limited for road transport. We also see that the model does invest in more than 1 million smart charging stations that are needed, again, to be in line with the large uptake of renewables for the electricity production. So they provide a large share of flexibility in the electricity system. Going to the industrial sectors, here the keywords are electrification, but also limited use of clean molecules. So this is one of the sectors where you do see that the 3 scenarios show you a different result by 2050. First of all, when you look at 2030, fossil fuels are still the dominant energy use in this sector. But when we look towards 2050, also here a lot of electrification will take place. Electrification through the use of industrial heat pumps, but also through electrifying in the chemical sector, electric cracking, for instance, in the steel sector. There's a lot of potential for electrification. We do see in some of the sectors where you do need a very high temperature that these clean molecules like hydrogen are needed. Up to 25% of the final energy demand in the industrial sectors will come from clean molecules. So a question then is, by 2030, does this mean when we still use fossil fuels as a dominant energy vector, do we still produce or emit a lot of CO2 emissions? Well, the answer there is no. At least if we can build this carbon capture and storage pipelines and infrastructure that is needed. So the model shows us that up to 17 million tons of CO2 can be captured in sectors like cement production, where you have these typical process emissions, but also for the refinery sector. For iron and steel sector, we do see that up to 17 million tons of CO2 emissions will be captured in a cost-effective scenario already by 2030. By 2050, you do see that CCS is to a more limited extent needed. So it's really like a transition technology for 20 years. Of course, question here is, will there be enough investors to invest in the pipelines that are needed to transport? By 2050, you will see that you need less of these infrastructure. Going a bit faster. For the power sector then, already showed you for the demand sectors, there's a lot of electricity demand. So that also means the power sector will need to produce more electricity. When you look at 2020 today, we do produce about 30, or we have a capacity of 30 gigawatts in Belgium. When we go to 2030, you do see that as a robust result. All three scenarios show us that the need for PV, or the capacity of PV solar panels, needs to go ×4, quadruple by 2030. For wind onshore, but also wind offshore, we see a doubling of the capacity in Belgium. Then looking at 2050, the three scenarios again show us a very different result. So when you look at the central scenario, the model goes almost to the full technical potential, which means 100 gigawatts that would be needed in Belgium on PV, 20 gigawatt of onshore wind and the 8 gigawatt of offshore wind. The model also shows you in the middle scenario, the electrification scenario, that when we give the model more access to offshore wind, the import from outside of the Belgian North Sea, this is a very cost-effective technology. So yes, up to the 16 gigawatt of offshore wind is invested in, and by 2050. But we also see that the model does invest in new nuclear capacity. So by 2050, up to 6 gigawatts of SMR technology is implemented as a cost-effective solution, even at a very high cost that we assumed for this technology. You also see that the need for renewables in this scenario, the middle scenario, is much less. Up to 50 gigawatt of PV, up to 10 of onshore wind we do need if we have access to more offshore wind and nuclear technology by 2050. This raises the question, where are we in 2030? Do we comply with this Fit for 55? And this is not one of the targets we have pushed into our model. The only target is we want to go to net zero, but it means in a cost-effective track, where are we in 2030? And then we see that, looking at the CO2 emissions, we can reduce up to 57% in Belgium if we manage to do all these hurdles, challenges, or opportunities, call it as you want. So for the building sector, is of course a lot of focus needed on renovation, up to 1.5 million heat pumps. Transport sector, the smart charging needs to be picked up as soon as possible, up to 2 million electric vehicles. For the industrial sectors, CCS is needed. For the power sector, a large increase in renewables. But we also see that green hydrogen will have a very limited role in 2030. And that's a bit in contrast to what the Commission is really pushing us forward now. Now, I want to take a sidestep up to a European scenario, work we are currently doing together with Concawe. So we asked the same question. When you look at the electrification need by 2030 in a European context, where are we then when we compare to the national energy and climate plans today? Is this aligned? So this very sharp increase in electricity, is it aligned with the supply that is foreseen in the national energy and climate plans of the member states? So let's first have a look at this slide. So it shows you the renewable electricity demand versus the supply. on a European frame. And in fact, there is a double ambition here. So today we produce about 1,000 terawatt hours of green electricity, renewable electricity. By 2030, we also need to replace a lot of fossil-based electricity that is produced today, more than 500 terawatt hours. On top of it, there is this increase from the building sector for the production of hydrogen, but also from the industrial sectors, more than 500 terawatt hours. And you see that the total demand for renewable electricity would be about 2,500 terawatt hours. When we then compare it to the supply side, you do see that we looked at the national plans, the recently submitted national plans, early 23. You do see that there is a gap of almost 500 terawatt hours in the national projections, including the existing measures. But even when we go to the national plans with the additional measures, so that go beyond what we already know today, there's still a gap of 250 terawatt hours. So the only plans or projections are from Ember and SOE that show us enough renewable electricity to comply with the demand that we project. Looking at the different member states, of course, you will see that there are member states where the national plans do comply, that are in line with what is needed to accomplish this fast electrification. But you also see that there's quite some countries, majority of the countries, that will not comply. That was for renewables. When we look at the complete electricity production, you do see that there's countries like France, for instance, which are a bit lacking short on the renewable side, but there's of course still nuclear production. Countries that have a bit of excess of electricity production, like France, but also Spain, Portugal, the Nordics. When you look at the trilateral region, Belgium, Netherlands, Germany, we really lack short. Even if we comply with the renewable plans, we still don't have enough electricity to fast electrify or to accomplish this fast electrification. So what is needed? Transport of electricity. And there we did look at the transmission grid operators plans, the NSOE plans. The gray lines here are the transmission lines that are already existing. The green, orange, and then also red lines are the ones that are projected. So projected from 2030 to 35, that's the green one, and so on. Key message here is that if we want to have this fast electrification happening, we need to realize these plans by 2030, not past 2035 or 2040, but even today. So a lot is needed to accomplish this electrification. Takes me back as the last 3 slides to the costs of this energy transition for Belgium. So I already told you that our model is always looking for a cost-optimal solution, least cost to 2050. When we look at the electricity generation cost, which is also a result of our model, we see that the electricity production cost will increase in all 3 scenarios. So we have more electricity demand, but also higher costs for electricity. That's not only for Belgium, it's for the whole Europe, Central Western Europe, the case because of the integrated market design. We also see that in the scenario where we allow the model to have more offshore wind imported in Belgium and the access to the SMR technology will bring us the lowest production cost of electricity, cost that goes up, but then slightly decreases and reaches a level of 56 euros per megawatt hour. Now, as a final result, the model also shows us what total costs are needed, the investment costs and operational costs to realize a net zero situation by 2050. And it's of course in the billions of euros, and these billions don't tell me much. So before I give you the final results of our modeling scenarios, I wanted to have a look at, or to put it a bit in perspective. And here on this slide I show you the universal energy subsidies that European member states have earmarked or have allocated to combat the energy crisis due to the Ukraine war. So in total, from September 21 up to January 23, almost 650 billion euros are allocated in the member states to combat the energy crisis. For Belgium, that was 9.4 billion euros, almost 2% of our GDP. When you look at Germany, it's more than 7% of their GDP. and more than 250 billion. And to be honest, it was not in the smartest way that we allocated these subsidies. So let's imagine we do this in a bit more smart way, in a cost-optimal way, for instance. And that brings me to the final slide, final results. So when you go to over 2030, so to reach 57% of CO2 emission reduction, we could achieve this at an annual cost of 2.5 up to 3 billion euros if we do it in the most cost-effective way. To 2050, costs will increase to 12 billion up to 21 billion, depending on the different scenarios, to reach net zero in Belgium, which is 2 to 4% of the total GDP today. And we also see that the electrification scenarios, more offshore wind by 2030 and the SMRs by 2050, will reach to the lowest costs for society in Belgium. Thanks for your attention. If you have more questions, feel free to have a look at our website.